Welcome to Team 21040's Design Day. Our sponsor is SRP, the Salt River Project, and our team consists of Nathan, Mark, Gabe, Jenna, and Vanessa. The Salt River Project has 3 evaporation ponds which measure how water efficient their 600 megawatt combined cycle power plant is. These ponds evaporate their wastewater, and due to EPA regulations, they are required to maintain a minimum of 2 feet freeboard. SRP's current depth measurement system consists of a permanently placed measuring stick with markings in the center of the pond and a person who uses binoculars to read the pond level. This is highly inaccurate and also raises safety concerns. They rely on the ability to read the measuring stick, but because the pond is filled with hazardous wastewater, they need to take a rowboat out on the pond to clean the stick frequently. Here's a view of their current measuring system from the binoculars to read the measuring stick in the pond. After doing research, we had 3 different approaches to solve SRP's problem. The first approach was an installed protractor and a sensor attached to it. The second approach was an ultrasonic sensor attached to the current permanently placed staff gauge. The third included a potentiometer. Looking over the pros and cons and speaking with our sponsor, we went with the protractor and sensor and have since then made it more sophisticated, including a solar panel and a NEMA enclosure that houses all of the electronics to transmit the depth data to a readily available website. Here's our trade analysis that helped us determine which approach to use. The protractor with sensor had the lowest risk.
The depth measuring system has 3 major requirements. It requires a high degree of accuracy, it is required to be self-powered, and it must be protected from its environment. In order to have 1-inch resolution on height measurements, the angle measurement must have a resolution of at least 0.058 degrees. This is met or exceeded by the electrolytic tilt sensor's 0.005 degree resolution. To ensure the system's power independence, the electronics function using the power and storage of the small solar panel and battery that are part of the system. In order to protect the system from the heat, water, and salinity of its environment, the electrical components are housed in a NEMA 4 enclosure with a small solar shade to prevent overheating, and the mechanical assembly has an enamel coating to prevent corrosion. The design of the depth measuring system is predicated on simple geometry. The DMS is permanently installed at a point on the shore of the evaporation pond with the vertical and horizontal distances to the existing staff gauge found through surveying. When operated, the arm of the DMS is pivoted to line up with the point where the existing staff gauge enters the water. This orientation is aided by an optic sight and a knob for holding the arm in place. With the arm in place, a triangle is constructed with the line of sight as the hypotenuse and the known distance between the staff gauge and the DMS as the bottom edge. Using the angle measured by the electrolytic tilt sensor and the tangent relationship, the height of the vertical side of the triangle is calculated and subtracted from the total height between the pivot and the bottom of the pond. This result is the depth of the water. This method yields a more consistent and more accurate measurement than the current method of measuring by eye. Additionally, because the system is entirely on land, it eliminates safety concerns associated with going out on the water to clean equipment.
After the depth measurement is acquired, the system then automatically sends the value to a web server. The DMS is equipped with the capability to connect to a 3G cellular network to access the internet. The web server is a means to bridge SRP's current data storage and our system together. The server can store all of the received depth values, each with a timestamp, and these measurements can then be easily exported into an Excel file to interface with the current storage system.
This summary shows the analysis done on the remote power as well as the pond liner. This table shows that our daily power usage totals up to 4.45 watt-hours per day, and our solar panel can generate up to 15 watt-hours on a cloudy day. To verify our pond liner analysis, we will install our system at least 5 feet away from the edge of the pond and will not exceed an installation depth of 1 foot. These analyses show that our system meets the remote power and pond liner requirements. To ensure our system can withstand the local environment, we have purchased and installed a NEMA 4X electrical box. Here you can see that both our mechanical and our electrical subsystems have been completed and are ready for system tests. Our depth data acquisition and transmission tests have all passed. We are able to find and transmit the pond depth in decimal feet, all under 10 minutes. And as of right now, we have passed all but one of our acceptance tests. The final accuracy performance test is being conducted within the week and will ensure our system can accurately measure a depth between a height of 0 to 13 feet and be accurate to plus or minus 1 inch. So far, the initial test results are promising.
Here's the list of deliverables agreed upon by our team and SRP. To keep them caught up, multiple design reviews and updates were held throughout the academic year. Along with that, all the information regarding how it works, how it is made, and how to operate it is also provided in document form. Last but not least, the physical system was installed at their site, ready to be used. Here's a video showing the operation of the DMS. After the protective cover is removed, the operator aligns the arm by targeting the intersection of the water height and the existing staff gauge. After the arm is locked in place, the power button is pushed. The operator then waits for the electrical system to convert the tilt angle into the depth. The depth is then transmitted to the web server. After completion, the operator can then replace the cover. The system is fully standalone with the power being supplied by its own solar generation.
Our DMS addresses safety issues expressed because it eliminates the need to clean the staff gauge in order to take measurements of the evaporation pond depth. The software of our DMS is protected by NEMA box and additional shade in order to protect it from various environmental concerns such as rain and extreme heat. A valuable lesson we learned while making our DMS was that fleshing out multiple ideas when designing a system, instead of going with whatever we come up with first, can be really helpful in creating a quality product. We also learned time management skills and the importance of working ahead. Because certain things pop up, we can't always predict how fast things will move along when they're out of our control. Lastly, we improved our communication skills because of how often we needed to consult SRP, Gary, and each other to create our final product. We'd like to thank Mo, Karsten, and Matt from the Salt River Project for being such amazing sponsors and being a proactive part of the design and installation process. Thank you, Gary, our volunteer panelists, and everyone in our 498 class for offering such helpful feedback throughout the academic year.